All right. Exponential and logarithmic equations. So we talked about how to simplify exponential and logarithmic expressions. Today we're going to move on to equations. And so basically an exponential equation is one which contains a variable in the exponent. You have two examples here of exponential equations. To solve exponential equations, we use the one-to-one property of exponential functions, and basically that says that if you can reduce an equation so that it looks like this, where you have the same bases, then the exponents have to equal the same, right? I mean, it's common sense. So if you have 3 to the x equals 3 to the 5, then x has to be 5. So we're going to use that property to reduce some of these and make them into the same exponent. All right, so in the first case, I have 4 to the x plus 2, 16 to the x minus 3. My bases are 4 and 16. All I need is for the bases to be the same, right? So they don't necessarily have to be, 2 to the power of something, just that they're the same. So I can reduce the 16 into a base of 4. So I can have 4 to the x plus 2 equal to, now 16 is 4 squared, right? And that's to the power of x minus 3. And once you have your bases the same, then you can set them equal to each other. Okay. So these, the exponents 4 squared and x minus 3 are multiplied by each other. So you have to put in the parentheses accordingly. All right. And now when I set those two equal to each other, I'm going to distribute the 2. Right? So 2 equals x minus 6. And x equals 8. Okay. The question of, do we need to plug in back into the original and check? Why not?
It's not anything that'll make it.
Right. The domain for these exponential functions is all real functions. So we don't have that risk of, is it going to make the denominator 0? Is it going to make, the radicand negative and so on? Okay. All right. Next, I have 2 over 3 and 9 over 4, right? So you see 2 over 3 and 9 over 4 are very closely related to each other. What is 9 over 4? So if this is 2 over 3 to the power of x minus 5, what's 9 over? It's the reciprocal of 2 over 3 squared, right? So 9 over 4 is just 2 over 3 but to the negative 2. Is that right? Yeah? To the power of 3x over 4. So now I have x minus 5 equal to negative 2 times 3x over 4. And when I cancel the 2's, x minus 5 is equal to negative 3x over 2. 2x minus 10 equals negative 3x. 5x equals 10. And x equals 2. And so if you quickly do check, right, if x equals 2 and I put it into the original function, I have 2/3 to the power of negative 3. And then 9 over 4 to the power of what? 3 over 2. And are those the same? Right? If you the 1/2 goes to take a square root, and then they are the same. Okay. So those are exponential equations. What about logarithmic equations? Well, if one is the inverse of the other, they basically follow the same properties, right? So in this case, the one-to-one property says if you have log with the same base, then you can set the arguments equal to each other. Oh, did I skip C and D? Oh my gosh, I skipped C and D. I thought that was quick. All right, let's do C and D. Aye. Okay. So what's the difference with C and D is that now I only have a power on one side of the equation and not on the other. So I have to eliminate the power here. All right. So for that, what I do is if I have 3 times x is equal to 6, what do? I divide by 3, and I do that because that is the inverse operation of multiplication, okay? So here, if I have an exponential function, the inverse operation of that is a logarithm, right? Now, in this 4 to the x here, I'm just going to rewrite it here to get more space. What is the base of the power? 4. So I need a logarithm with the same base. And whatever I do to one side, I have to do to the other. Meaning, this side reduces to x equal to log base 4 of 13. And if this is a non-calculator section, this is a good enough answer. Log base 4 of 13. However, if we do want to put it in decimal form, go ahead and do that for me and let me know what it is. Okay, so this is 1.850. All right. The other way of doing the same thing, right? If I have 4 to the x equals 13, yes, you can just write it in terms of logarithms. So let's write this as a logarithm. Log base 4 of 13 is equal to x, right? And you see how you come up with the same situation. Okay, so just writing it as a logarithmic form. All right, why don't we do that for this next one? Here I have e to the 2x plus 1, so I'm going to use an ln. So let's just rewrite it as an ln. All right, so ln of the power, which is what? 2x plus 1, has to equal the, I'm sorry. Ln of the power, which is 8, has to equal the exponent 2x plus 1. So
The exponent's what it equals.
right. So the answer to a logarithm is always the exponent that goes here. What's the base of the ln? E, and the power is 8. So in this case, I have ln of 8 is equal to 2x plus 1. I subtract 1, so I have ln of 8 minus 1 is equal to 2x. And please be careful, this is not ln of 7, right? This is ln of 8 after you take the ln minus 1. And now I need to divide everything by 2. So x is ln of 8 minus 1 over 2. You can have an answer like that. Okay. Yeah. So if you do plug this in the calculator, what is it? $0.540. Okay, now let me show you a little bit of how we can manipulate that expression a little bit further. I can rewrite that exact same thing as ln of 8 over 2 minus 1/2. Yes? Okay, which means this is just half ln of 8 minus 1/2, right? Just rewriting it. And so now, using the properties of logarithms, can I make the 1/2 an exponent here? Why not? Of course I can. So that'll be ln of 8 to the 1/2 minus 1/2. And what is that? Right, so it's ln of, 2 root 2 minus 1/2, or ln of root 8 minus 1/2, and so on.
So what do you want us to do?
Okay, so hang on. I'll go there in a minute. Now, can we simplify this? Can we expand this even further? We can expand it to ln of 2 plus ln of root 2 minus a half. Is that right? Because what we did yesterday was ln of 2 root 2. You can expand it to ln of a plus ln of b. Remember what we were doing in yesterday's homework? And now this is ln of 2 plus half ln of 2 minus 1/2. So do you see all of the different ways of writing them? Why is this half ln of 2? Right, it's the power. Okay, so now going back to the question of how do I write it on the test? Okay, so on the test, if I were simplifying this, I would leave it like this, or I would leave it like this. However, what if you are taking a multiple choice test and this question shows up on the multiple choice test? Any of those other options can show up as a choice, right? So let's go back to what I've been saying all along throughout the year. Precalc Honors is not about this is the answer, 0.540. No, we can all do that. There is always some sort of online like website that I can plug in a function and get an answer. We are not doing that here. This is about this holistic understanding. Okay? Do I recognize that this and this and this and this and this are all different forms of the same thing? This is what I'm trying to get at here. Okay? All right. So let's move on then to logarithms, logarithmic equations. So if I have a logarithm with the same base, then I can set the arguments. These things inside are called the arguments of the logarithm. I can set them equal to each other. All right? Okay, so let's go here. I have 2 ln of x equal to 18. Let's divide by 2. So now I have ln of x is equal to 9. Now, I'm going to use the inverse property here. This is a logarithm, which means I can rewrite it as an exponential form, right? So, what is the base here? E. Every base needs an exponent. What's the exponent? 9 equal to x, right? So you see how we can just immediately solve it. X equals e to the 9. You can either leave it like that. In fact, just leave it like that because, okay, rule of thumb, once you get into the 4-digit numbers, right, like the thousands, you don't have to simplify anymore. E to the 9 is just fine, okay? Because these numbers can get very large very quickly. Okay, here let's subtract 7. And I get negative 3 log 10x equals 6. Divide by negative 3. Log 10x is equal to 2. Now, where is the negative 2? Where is the exponent here? Negative 2. All right. Every exponent needs a base. What's the base? 10. 10 to the negative 2 is equal to 10x. So, if I divide by 10, x is how much? 10 to the negative 3, which is how much? 1 over 1,000. Okay.
Wait, why does it become 10 to the negative 3?
All right, so I have 10 to the negative 2 over 10, right? This is a 1, right? So this is 10 to the negative 2 minus 1, which is 10 to the negative 3. Okay. All right. Next one. What's the exponent here? 20. Base is 5. So 5 to the 20 is equal to x to the 4. All right. So now raise this to the power of 1/4, and raise this to the power of 1/4. So x is 5 to the power of 5. Correct. Okay, whatever the exponent is, you have to raise it to the power of the reciprocal. Yeah.
So for this one, you're trying to get rid of the
Logarithm.
But for the 4 to the x equals 13, you tried.
For which one? But that's 4 to the x equals 13. The x was the exponent. Here,
Oh, okay.
okay? Yeah.
Did you want us to write what 5 to the power of 20 is?
That's too big, isn't it?
I mean, you can wait for it.
Yeah, like I said, once you get into the thousands, you can just leave it as the power.
Unless it's 10. Or it's 10.
I mean, yeah. Okay, here I have log base 5, so I can set the arguments equal to each other. And I get x squared plus x equals 20. And that is just a quadratic function. X squared minus plus x minus 20 equal to 0. Can we factor this?
Yeah.
And I get x equals -5, x equals +4. Now, is the domain for logarithms all reals? No. So here we do have the potential of getting extraneous solutions. That means you have to plug them back in and get a solution and see if it checks out, right? You have to plug it in to the very, very original here. Okay? So plug in here. And so when you want to check x equals -5, you get log base 5. -5 squared is 25 plus 5. I'm sorry, minus 5. Is that equal to log base 5 of 20? That is, so that works. Next, x equals 4. It's going to be log base 5, 16 plus 4. And that's also the same as log base 5 of 20. So both of these work. All right, next, take a look at this one. Okay, now here I have 1 log on one side of the equation, but 2 on the opposite side. In this case, I need to condense because I can only have 1 logarithm on either side, right? So first condense. So I have log base 2 of 5 equal to log base 2 of 10 over x minus 4. I set these two equal to each other. Cross multiply. 5 times x minus 4 equals 10. 5x minus 20 equals 10. 5x equals 30, so x is 6.
So we don't have to check these.
You do.
Wait, then why didn't we check? Oh, never mind.
Yeah. So if I do plug in log, x equals 6 into here, I have log base 2 of 5 equal to log base 2. Now, you haven't really changed the problem in going from the first step to this condensing step. So you can plug it into either of these, right? So here, 10 over 6 minus 4, it's 5. So yes, that works. Yeah.
Let's say it was like log base 3 of 5. Is there literally nothing you could do?
Yeah.
Okay, and then if it was like log base 3 of 10 minus log base 2, do you still do the division thing, or you can only do the division thing if they're the same?
You have to, the whole thing only works if they're all the same base.
But if you put in your calculator log base 3 of 10 over log base 2 of x minus 4. Oh, wait, you can't put x. That's like, let's say you did log base 2 of 10 over log base 2 of 3. Would it not calculate it?
No, it will calculate it, but you can't solve an equation
Oh, okay.
if they're not in the same
Okay.
base. Yeah. Okay. This next one, again, it says solve for y. This is another one of those problems where it's not in your book, but you do need to be able to manipulate these equations in terms of one variable for calculus, and so I've put them in here. If we want to solve for y, this is a function as ln of y, so we have to write it in exponential form, all right? What is the base here? E. And what is the exponent? Negative 5x plus 3, and that equals to y. Okay? All right.
That's it?
That's it. Oh, yeah, I mean, no, that's it for that problem. Yeah. Okay. Now, we've got these two problems here, A and B, that are exponential functions, but with different bases. All right? What we're going to do here is basically we can use what is called change of base formula. So what we're going to do is, to get rid of them, we're going to take logarithms of both sides. All right? Because they have different bases, it doesn't matter. No matter what logarithm we take, is going to have a different base. So what we're going to do, either you can take log base 10 or ln. I'm going to do ln. So let's take ln of both sides. Now what I have is ln of, write small because these can take up a lot of room. 3 to the power of 6x minus 3 equals ln 2 to the power of 4 minus 4x. I just prefer ln. Now, the exponents can come down, right? So I get 6x minus 3 in parentheses times ln of 3 equal to 4 minus 4x ln of 2. Okay. Now I'm going to distribute the ln's. So I'm going to get 6x ln of 3 minus 3 ln of 3 equal to 4 ln of 2 minus 4x ln of 2. Okay, now if I need to solve for x, I need to collect all the terms with the x's on one side, everything else on the other side. So I'm going to get 6x ln of 3 plus 4x ln of 2 equal to 4 ln of 2 plus 3 ln of 3. You guys with me so far? Okay. I'm going to factor out an x. Don't factor out a 2x. There's no need. Just factor out an x. And I get 6 ln of 3 plus 4 ln of 2 equal to 4 ln of 2 plus 3 ln of 3. Did you guys do this in Algebra 2 last year? No.
We did like ln.
We did.
I don't think we did.
Okay. All right. I need to. Okay. All right. Now what do we do?
Now we put it in a calculator.
No. Because this is on the non-calculator section.
Divide.
We're going to divide by this, right? Divide by 6 ln of 3 and so on. So x is 4 ln of 2 plus 3 ln of 3 over 6 ln of 3 plus 4 ln of 2. And just when you think you're done, you're not. Because now we need to simplify this a little bit more. Okay? The exponent, the coefficients will now become exponents. And so I'm going to condense this, and it's going to be x equal to ln of 2 to the 4 plus ln of 3 cubed over ln of 3 to the 6 times ln of 2 to the 4. I'm running out of space.
Oh, it's time?
Plus, sorry. Plus.
Wait, can it be time?
Now we're gonna simplify even further and condense. So it'll be ln of 2 to the 4, 3 cubed over ln of 3 to the 6, 2 to the 4th. And now at this step, right? So here I have ln of 2 to the 4, which is 16, times 3 cubed, which is 27. How much is that? 16 times 27.
The answer is 189.
Oh my God, it was listening to me. That is so not cool. When we plug them into the calculator, these are the values we get. Now, for my purposes, these numbers are way too large. Like the 11,000 is way too large. Again, once you see that you're getting into the thousands, you don't have to simplify anymore, which means this is a good enough answer. Now, the question was, can we cancel the 2 to the 4th? And the answer is absolutely not, because this is an argument of the ln. So it's ln of all that, and it's ln of all this. And we cannot by any means simplify. That's like if I had sine of 3x over cosine of 3x. I can't cancel those 3x's, right? They're arguments inside another function. Yeah.
Wait, one question. But those have the same beginning. Like they both start with that.
Still. So if I had sine of 6x and I had sine of 6x, can I cancel out the 6x? Or, well, that's if I had sine of 3x, can I cancel out the 6 and the 3? I cannot.
They're the same. The two are the same.
Yeah, but you still can't.
Okay. And then also are all questions on the calculator section gonna end in a decimal, or do some still end like not?
If you have the calculator, I'll probably just say to, do a decimal. But you know, huh?
What would it be if it's not decimal? What's the phrase?
Exact form. Leave the answer in exact form. It will say leave the answer in like simplified, logarithmic form or something. Okay? All right. Let's do another one. I'm going to take ln of both sides. The 2x plus 4 will come down. So I get 2x plus 4 ln of 6 equals negative x plus 1 ln of 5. Believe it or not, a very common mistake is not placing the parentheses here, and then you distribute incorrectly. So now I get 2x ln of 6 plus 4 ln of 6 negative x ln of 5 plus 1 ln of 5. Collect the x's, or the terms with the x's. So 2x ln of x plus x ln of 5 equals ln of 5 minus 4 ln of 6. I can take out an x. I missed something here. It's ln of 6. And I get 2 ln of 6 plus ln of 5 equals ln of 5 minus 4 ln of 6. So now I have x equal to ln of 5 minus 4 ln of 6 over 2 ln of 6 plus ln of 5. Are we good? Okay, I'm going to condense. This is going to be ln of. Can I combine some steps here? It's going to be 5 over what? The
5 over 4.
6 to the 4.
Wait, why not? Oh, okay.
Okay? Over the 2 here will come up, so it'll be ln of 6 squared times what? 5. Okay? And I'm fine with this. We can simplify the denominator. So it's ln of 5 over 6 to the 4 over ln of 36 times 5 is what? 180. Okay? Yeah. Again, if it's within the hundreds, like if it's a 3-digit number, please simplify. Okay? So, all right. So sometimes you will get something here, you know, like 5 over, let's say, something that you can reduce, and you have to reduce those, right? Okay. And again, if this was a multiple choice question, right? If you come across a multiple choice question, you can see this in different forms. So it's important for us to be able to like distinguish equivalent forms. Okay? All right, let's go to one more. Okay, here we have an e to the x. It's an exponential function. But look at the form of this. We've done some with quadratic form before, right? So let's take a look at some quadratic equations. What does a quadratic equation look like? An example would be x squared minus x plus 3, right? Equals 0. That's a quadratic equation. What makes it a quadratic equation is it's in the form ax squared plus bx plus c. So what is it that we have here? Whoops. What is it that we have here? We have a constant, right? Then we have a variable to the power of 1. Then we have a variable to the power of 1. And then another variable where the exponent is twice the first one. Okay, so this is 1 times 2, 2. So similarly, I could have x to the 4. Guys, please. Okay, similarly, I have x to the 4 minus x squared plus 3. Why is this quadratic? Because if this is a 2, this is twice that, right? So now what do we have here? I have e to the x. The exponent is x. But here the exponent is twice that, 2x. So I can factor this using quadratic form. And the way to do that is this. I'm going to get 2 parentheses like this. And here I need 2 numbers that multiply to e to the 2x. And that's e to the x and e to the x. All right? Now I can go about it, you know, the same exact way. 2 numbers that multiply to -2 but add to -1 is positive 1 and -2. Right? So now I have 2 mini equations that I can solve on their own. This is the zero product property. One thing times another thing equals 0. This is when I can simplify, right? 1 equal to 0, which means e to the x is equal to -1, right? And this is an ln, yes? So ln of what? -1 is equal to x. But what is ln of -1? No solution. We could have already known that because what exponent for e would give us -1? None. All right, so next I have e to the x is equal, -2 equals 0. So e to the x is equal to 2. And now I need a logarithm with a base e of 2 equal to the exponent x. So x's ln of 2 is an acceptable answer, or x is approximately what? What's ln of 2? 9.3, right. Okay? All right. No, I just, eventually, when you're my age, you just know that ln of 2 is just 0.693. Just like e squared is 7.4. Okay, plus 3. Here we're going to add 3 to both sides. 40 e to the 0.67. X is 230. 0.6x, sorry. Yeah. Oh my. Okay, so 40, we're going to divide by 40. So e to the 0.6x is 6. And now again, this is a logarithm with a base e of 6. It equals the exponent. And now I can divide by 0.6. So x is ln of 6 over 0.6. And how much is that? $2.986. Okay. All right, go ahead and start on the next one. All right, I'll give you a few minutes. Right, so for this one, we do have to condense, and then it becomes a quadratic equation. We get 2 that come out of the math, but 1 negative half is extraneous, so you have to throw it away. All right, now, the next one, we're not going to do it all the way. We're just going to, I'm going to stop at some point. So this is log base 12 of 12x, x minus 1 is equal to 12, right? Okay, so now this is a logarithmic equation. Let's write it in exponential form. The base is 12. Every base needs an exponent, which is 12, equal to 12x minus times x minus 1. So here we have 12 to the 12, which is a very large number, and I'm going to leave it that way, equals 12x squared minus 12 x, right? And honestly, we could just leave it that way. What you can do is divide everything by 12. And so then what does that equal to? 12 to the 11 equals x squared minus x. And we are not going to factor that one. Okay? Because 12 to the 11 is a very, 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 very large number. However, I can possibly give you a problem where, let's say, this, instead of like 12 to the 11, it might be, let's say, I don't know, some weird like 493 equals x squared minus x. And would you be able to solve that with your calculator if you graphed it? Yes? How would you do that? What would you have to find the zeros, or you graph x squared minus x in F1, 493 in F2, adjust the windows and see where they intersect. Either way, you can use your calculator to graph it. So why do I even, bother with things like this? To show you that they're not always going to be cute little numbers like 3 and 1/2, right? I just made it up.
Oh.
Yeah, so suppose. Then you can use your calculator. Okay? Now, the homework for this is this one. And you can start now. It will be due Monday, and Tuesday's your test.